Welcome back, everyone. We finished talking about inverse functions. Now we'll talk about exponential functions. And the next section will be on logarithmic functions. And those two are inverse functions, so that's why we started this chapter with inverse functions. So what about exponential functions? You've heard about exponents before, you've worked with them before. So let's get going here. As soon as I find my pen, where we go? There we go. Okay. I should certainly mark that up, didn't I? All right, exponential functions. We don't need to see this slide. And let me make a small adjustment here. There we go. All right. So the definition of an exponent. First of all, we're going to talk about a real number A. We're going to stick with positive ones. And we're going to talk first about this, what might look like a crazy one to you if you haven't seen it before. We're going to take that A as a base. By the way, we're not going to bother with 1. It doesn't do anything at any exponent. So A to the m over n power. Example, A to the 6th over 5 power. What does that represent? Well, the top represents an exponent, a regular integer exponent, and the bottom represents a root, like the 5th root in this case. And you have your choice if someone tells you what that number A is for the base. You can either do this. You can take the 5th root of A and then multiply that by itself 6 times. Or you can do it in the reverse order. You can take A to the 6th and then take the 5th root of it, whichever is convenient. Typically, though, hint, typically you want to go this way. Take the root first and then take the exponent, the integer exponent of that. Let me get rid of the pen here for a second. There, erase the ink so we can actually see what's going on. All right, make sure the pen's still good. All right, so here's an example. We have 16 to the 3/4 power. Remember, that means to the 3rd power to the 4th root. And my suggestion, if you remember from just a minute ago, is take the root first and then operate on the power. So take the 4th root of 16, that's a 2, then cube it, and there's our answer. This is the 3/4 power of 16. Another example, 27 to the minus 1/3 power. I'm going to sneak down here, or no, up here, because I think there's another one coming. So 27 to the minus 1/3 power. First of all, there's a minus there, so we're going to take care of that even before anything else. Minus means you've got 1 over 27 to the 1/3 power. All right? So in the exponent, the numerator means we're going to take 27 to the 1st power. I guess we can ignore that, can't we? But we have to take the 3rd root. So what we're going to do is 27's in the denominator, and we're going to take the cube root of 27, which is 3. So 1/3 is your answer for this one. That's how we get it. Another one, notice the minus sign. That means we're going to put that 64 to the 1/2 in the denominator. The 1 means the 1st power. We can ignore that 64 to the first power is 64. And this means we'll take the square root of it, which you can see right there. So our answer is 1/8. And we're also going to include not just fractions, but any real number as a power of a. So it could be the square root of 3 even. A little bit strange, but we can still do it as long as your exponent is a real number. So we could have, if we wanted that square root of 3, where am I here? 2 to the square root of 3. If we wanted to use rational exponents, we could get closer and closer approximations to the square root of 3. This would be 17 over 10. That's closer to it. And then eventually get something close enough for our purposes. And there is the cube root of 3 power of 2. It's hard to say, isn't it? Cube root of 3 power of 2. So what does this look like? Well, we can go back to our roots and see what this looks like graphically. If we talk about just using integers, then our graph looks like this. 2 to the power x. Using just the integers. So we have individual dots, and we can see how that graph is progressing. Second, what if we use rational numbers as our domain? That means we use all the fractions possible, and we use those as exponents of 2. And we get a bunch of holes, but we can see that we're closing in on that curve pretty much. And then if we include all real numbers, then the curve becomes a smooth one. We're going to use some rules and theorems, and they're going to be good for all real numbers, even if they're square roots or even pi. All of those will be good. Now you want to get those properties and rules down because we're going to be using them the whole chapter. In fact, if you remember this 3-word phrase, logarithms are exponents. So even when we get to the next section on logarithms, we're still talking about exponents. They'll look a little bit different, but they're still using the rules and properties of exponents. Now, some properties of exponents that you need to remember, because this is a little bit different perhaps than what you've seen before. First of all, you've got a number a, and it's positive, and we're not going to bother with number 1. So we're going to take the numbers from 0 to 1, not including the 1, and we'll take the numbers to the right of that, and those are all the numbers we're going to use. Plenty there. Now, that said, if we use x as our exponent, that gives us a unique real number for our function, our exponential function. One of those properties is not only do you get a unique real number, but also if you use that base 2 different ways and end up with the same number, that means the 2 bases must have been the same. So we can work backwards, and sometimes that's helpful. We'll have some examples of how you can use that. Not right away, we'll get there. Well, why not? So let's say 6 to the square equals 6 to the triangle. That means the square and the triangle are the same number. If we had 6 to the 2x, for example, equals 6 to the minus x plus 2, then that means 2x equals minus x plus 2. That's what we're going to use. Third, another property. Now, we're splitting this into two parts. These two actually go together, but they're separate. If a is bigger than 1, then if m is less than n, that means m is the first left to right on your graph. Then m, since this is a smaller number, you're going to end up with a smaller result from using your exponent. If a is from 0 to 1, the opposite holds. M is smaller than n, but m actually is bigger than a to the n. So remember, a has to be positive, and we're not using an a of 1 either. Remember, we're not going to use negative numbers. That's out. And we're not going to use 1. Okay, let's move on from this. So, when a is above 1 or greater than 1, then we're going to have an increasing function, sort of like that. When a is between 0 and 1, in other words, you might think of that as a fraction, like 5/6 or 1/2, then it's going to be a decreasing function, and it will look something like this. Sort of like the first one over here, but flipped, left to right. Here's how we can use it. First of all, let's get familiar with exponents. We're using a base of 2 in this case. X is the exponent, and f of -1 means we're going to use -1 for our x. So I have 2 to the -1. And negative means we're going to use the reciprocal. So I have 1 over 2 to the 1, or just 1/2. Next, let's try again. We're using the same function, 2 to the x. This time we're going to put a 3 where the x is. So this will be 2 to the third, and that's 2 times 2 times 2. There's your answer. Next, let's put a 5/2 there. So equal to 2 to the 5/2. And you can see it below there, but stick with me. So we're going to take 2 to the 5th power. Now this is the opposite of what I told you is usually the case. This is a bit of an exception, although we could do it both ways. And then we'll take the 1/2 power. Notice it's a power to a power, so we multiply the exponents, that gives us the 5/2. We're going to take 2 to the 5th power, which is 32. Then we'll take the square root of that. We can write it like this. Now notice 16 is a perfect square, and it divides into 32. In fact, it's the biggest one that will. So we can split the square root of 32 into the square root of 16 times the square root of 2. Why do we do that? Because this part will come out even. The square root of 16 is a 4, so our final answer is 4 square root of 2, as you can see below here. Next, you'll have to use your calculator for this. There's no way of getting around this, really. We just take 2 to the 4.92, and you have to use your calculator. 2, use the caret, put 4.92, hit the enter, and there's your result. To the nearest thousandth, that is. If you actually look on your calculator, you should see a bunch of other decimal places. All right, so a greater than 0, as always. We don't bother with 1. there is our basic function, a to the x. F means it's a function. We don't use 1 because then it would be a constant. It would always be 1. Constant functions aren't interesting. Now, how about some of the properties of exponential functions? You might want to make a note of a couple of these. First of all, as long as you got a to the x, remember a is positive, one thing you can always count on, regardless of what a actually is, 7, 15, even 1.3, the y-intercept is always going to be 0, 1, just like we have over here, regardless of what the base is. Second, because on the left-hand side, this blue curve approaches the x-axis without ever touching, it's called a horizontal asymptote because it approaches the x-axis closer and closer and closer, but asymptotes don't actually touch it. They just get closer and closer and closer. Third, the domain is all real numbers. So if you look at this graph, there are going to be parts of the graph out here, there are going to be parts of the graph out here forever in both directions. So the domain is all real numbers. And if you notice what y values, well, remember back here, it approaches the x-axis but never touches it. So our range starts near 0, and as you can see, it climbs up and up and up in the direction of positive infinity. Also, lastly, the function is increasing, and we're looking at this blue curve. If you look at it from left to right, it's increasing, where the y's are getting bigger and bigger, or it's rising. It's increasing on the entire domain, and it's 1 to 1. Why is it 1 to 1? First of all, it's a function because it passes the vertical line test. Second, it's 1 to 1 because it also passes the horizontal line test. Now, I've got several slides here that talk about individual parts of that. Now remember, in this first one, we're talking about f of x equals a to the x, and in particular, we're talking about bases that are greater than 1. If they're greater than 1, then that function is increasing and continuous. You can draw it without lifting your pencil or pen while you're graphing it. Another one, the x-axis is a horizontal asymptote. See, it gets closer and closer to the x-axis, but it's never going to touch it, even though it gets very, very close. Next, it passes through these 3 points. Now this is rather amazing in a way, because even if we don't know what A is, as long as it's positive, then the graph is going to go through these points. The first one you want to remember is it goes through 0, 1. Second, it goes through 1A. So if this A is a 2, it goes through 1, 2. If A is a 7, it goes through 1, 7, and so on. And third point is always -1, then the reciprocal of A. 3 points you can count on for any exponential function. Next, now that was if it is greater than 1. If it's between 0 and 1, things change. Notice back here, it's rising to the right. Here, it's decreasing or getting lower to the right. Again, it's asymptotic to the x-axis. It continues getting closer and closer, but never touches that x-axis. So it's going to be decreasing because it's getting lower and lower, and it's also continuous because you can draw your graph without lifting your pencil or pen. Again, the x-axis is an asymptote, just on the other side this time. Same points we had before. If your base is A, you're going to have an automatic 3 points. 0, 1, regardless. 1A, regardless of what A is. And -1, reciprocal of A. Guaranteed for your basic exponential function. So here is a sort of a summary of those things. This is where A is larger than 1. And this is what it looks like if A is between 0 and 1. Also known maybe as a fraction, sort of, even though 6 over 2 is really a fraction, but we're talking about fractions where it's not an improper fraction. Proper fraction. So this is typical of having a base greater than 1. This one is typical when you have a base between 0 and 1. This is a good one to pause on. Take a look. On this side, the green, red, and blue curves are for A's greater than 1. On the left side, use a bracket for this one, these A's are between 0 and 1, so they're decreasing functions. Notice also that we've got somewhat similar or related bases, but just on different parts of the number line. What we have here with the green one on this side is just a flip over the y-axis. If you look at the red curve here, flip it over the y-axis, we've got the other one. The blue one, flip it over the y-axis, there you go. Just flip it like as if you're twisting the y-axis 180 degrees. So some characteristics we've just gone over. Here's a summary. 3 points are automatic. For your base of A, you get the point -1 reciprocal of A. You get 0, 1 always, and 1A, regardless of what kind of A you have. If it's greater than 1, you'll have an increasing function. If it's between 0 and 1, it's going to be decreasing. The x-axis in both cases is a horizontal asymptote. That's for your exponential functions. The domain is all real numbers, and the range is just the positive numbers. Next, what's the domain and range? Well, take a look at it. Domain, all real numbers. Range, all positive numbers for all exponential functions. Take a look at this. Show the graph of this. Here's where it would be a good idea to pause, grab your calculator, graph this function, and at the same time graph this function. Remember, they're just a little bit different, but I want you to see the difference between those two. Graph this one first, take a look at it, and graph this one. Don't replace it. So use y sub 1 for this one, use y sub 2 for this one, so they'll both show when you hit the graph key on your calculator. you'll see, if you did that, that the graph is reflected about the x-axis. Why? Because this minus sign in front of the exponential function. This basically turns the original graph, this one, upside down. Still, the domain is all the real numbers, but because we turned it upside down, 0 to infinity becomes negative infinity to 0 because it's on the other side of the x-axis. Here's the original, here's with the minus over here. Well, what if we have a function like this? So we've started out 2 to the x is our basic, but we've decided x is boring. We'll make the exponent, where's my, there we go. We'll make the exponent x plus 3. What does that do? Well, I want to remind you that if you have g of x, and remember the x squared function, if we make this x minus 3, for example, instead of just x, this moves this one to the right 3 units. If we had h of x, and we had x plus 5 squared, then that moves your original graph, this one, to the left 5 places. If I put a minus in front of this one, then it takes what we just moved to the right 3 units and turns it upside down. And over here, if we put a minus in front of this, the graph we moved left 5 units is turned upside down over the x-axis. And there's some pictures of these. This is the original one here. That's the black one. And the blue one is the graph of 2 to the x plus 3. Notice it's a plus 3, so it moves it in the opposite direction of this sign right here. So how about this one? We've talked about things like this before. We just mentioned about what would happen if we change the x to an x minus something or an x plus something. Remember, this is like adding or subtracting a k at the end after using the basic function. So, excuse me, this one, the x minus 2, is going to move 2 to the x 2 units to the right. And what's this going to do? Remember, that's vertical, so it's going to move it downward 1 unit. So you start with this function, 2 to the x. You're going to move it over 2, and you're going to move it down 1 before you stop. And there's a picture. If you look at that point, where is my cursor here? Okay, here's the original. If you look at the 0, 1, that's a good starting point. What happens to that point? Well, what we just said is it moves it to the right 2, and the minus 1 moves it down 1. And there you go. So 0, 1 is a good reference point. Gives you an idea of what translation happens. How about this one? Write it using a common base. What would be the common base? Well, over on the left-hand side, of course, we won't use the 1. That wouldn't make any sense. We're going to use 3. So what is the left-hand side using that 3? Well, since 3 is in the denominator, it will be 3 to the minus x. So we figured out that 3 is going to be the base we want on the right-hand side. So 81 is 3 to what power? Well, grab your calculator if you need to, or better yet, do it in your head. 3 to the first, 3 to the second, 3 to the third, until you end up with 81. In this case, it's 3 to the fourth power is 81. Now, you want to solve this. One of the properties is, if we've got a base to, say, the x power, and it's equal to the same base to the y power, that means x and y are the same. We'll use that property up here, and that means the negative of x equals 4. The exponents are the same, since we ended up with 2 equal amounts. Minus x equals 4, so x is a negative 4. Check that for yourself. That's a good one to throw in the calculator. Do it real fast. If you do it manually, that's even better. So there's our original. 1 over 3 is 3 to the minus 1. And there's our x power. So we had 3 minus 1 to the x power, multiply the exponents, and this is what you get. And on the other side, 81 is 3 to the fourth power. You've got minus x, and now you've got x. So there's the solution set. Now up here it said solve, so you have two choices. You can write x equals negative 4 because it just said solve it. Or you might just put it in a box like this. There's your solution. Or you might want to use set notation and say negative 4 is in our solution set. How about this one? How about pausing it? Can you do this by yourself? Come on back when you're finished, or at least give it a shot. All right, now 2 and 8, that should sound a little bit familiar. 8 is 2 cubed, so here's our left side intact. The right side, here is 8 using an exponent. Still got the x minus 6. Sorry about that, folks. Next, we've got a power to a power on the right, so 2 to the x plus 4 equals 2 to the, multiply the 3 times the x and the 6, 3x minus 18. And now you know the rule. That means this exponent must be equal to this exponent. And we just solve that equation. Subtract 2x from both sides, 1x from both sides. We'll have 2x here. Add 18 to both sides, and we'll have 22 here. So x equals 11 after we divide by 2. And that's our solution. You can write it this way, or you can write as a solution set like that. We're going to clear so we don't get a mess coming up here. So here's what the slides tell us. And hopefully they do it basically the same way. And sure enough, it looks the same as what I did. They did it slightly different, but in an equivalent fashion. And there's the x that we found by ourselves. All right, we're getting to something a little interesting here. We've got fractional exponents. How are we going to solve this? Well, remember, a power to a power. You multiply the exponents. Keep that in mind. Now over here we've got x to the 4/3, but what we want is x by itself. Well, we can use this property to make that happen. Here's our x to the 4/3. We want it to be x to the first. Well, if I multiply it by 3/4, the exponent, I'm going to get x by itself. Of course, I have to do that on both sides, so I'll have 81 to the 3/4 as well. On the left-hand side, the 4's cancel, the 3's cancel. I've got x to the first power, or just x. On the right side, now here's where my tip earlier comes into play. You can work this two different ways. You can take 81 to the 3rd power. I'll let you figure out what that is. I'm not going to grab my calculator to do that. Pretty big number though. And then when you have that finished, then you'll take the 4th root. And good luck with that, right? That's not going to be too easy. However, if you take my advice, which usually is helpful, take the root first, and then take the power afterward. The 4th root of 81 is 3, and we still have the cube, and so our x is 27. Don't forget, check it out. Take 27 to the 4/3 power, and make sure you end up with 81. So remember, 27. If you're using a TI-83, for example, hit that caret sign, make it 4 divided by 3, and you should end up with an 81. They basically did it the same way, except they used the cube root symbol. And why do they say plus or minus 3? Good question. Let's clear our ink. Here we go. Clear the ink on that slide. Now what did they do? Well, notice that they took the cube root of x and taken that to the 4th power. So here they cubed, no, they took the 4th root of each side. Sort of unusual, but because they're taking the 4th root, that means you're going to get 2 answers instead of 1. Remember, even roots, two solutions. Okay, got that? Make a note to yourself. Check both solutions. Make sure you check each one carefully. Now, an alternate way. And this almost the way I did it, but not quite. What they're doing is cubing it first to get to x to the 4th power, and that'll be 3 to the 12th power. Then you're going to take the 4th root. Here's we get the plus or minus, because you're taking an even root. One more time. even root 2 solutions. 2 solutions. There we go. Of course, that 3 cubed is 27. There are your 2 answers. Just make sure you don't think of this as one answer. It's the shorthand way of saying x equals 27, and x could be a negative 27. Both those will work in the original equation. Now we're going to get the compound interest, a little bit of money here, so maybe this will get some of you going a little bit stronger. Here's what the formula looks like. First of all, this says interest equals principal times rate times time. What does that mean? You're depositing this amount at this annual rate for this number of years. And this is the amount of interest you're going to get. Now, what is waiting for you when you get back to the bank to collect that interest? What you have is the money you put in to begin with, and if you waited 1 year, then this is just P times R times 1. And if you factor out the P, it's just P times 1 plus R. Remember, this is for 1 year. 1 year. Now, what about the next year? Well, next time, you already have this. That'll be your new principal. And you multiply that times 1 plus R. And that's what this looks like. Shortened, it looks like that. For 2 years with an annual interest rate of R, or as a percentage most likely. At the end of the 3rd year, you got P times 1 plus R cubed. Remember, the 3 represents years that investment is making money for you. If you continue like this, or leave your money in longer, here's a formula, but don't memorize this one. Nice formula. However, it's not the one to remember because this is a specific one. This is for when it's compounded annually. If it's compounded semi-annually or monthly or something else, this one won't do the job for you. What you want is this formula right here. And it'll work for the annual one as well. Now, the way I typically write it, and you can choose which way you want to do it. Where's my mark there? The way I write this is I write A equals, it's not too much different. Again, the 1 is there. Again, the annual rate divided by n, and n represents how often every year that the interest is compounded. But instead of Tn at the top, I put Nt. Not a big difference, but most of the books that I've seen write this as Nt as the exponent. One thing to keep in mind is that as soon as you write this n here in the denominator, the next job you're going to do is put an n up here too. That's one thing I like about it. As soon as you write the n down once, remember it's also going to go in the exponent, and that will go times the number of years. Here's an example. Now remember, A equals P, that's the principal, that's the amount you're investing, 1 plus R over N to the NT. All we have to do is fill in the blanks. It says, suppose that's deposited in an account paying 4% per year, so it's per year, compounded quarterly, 4 times a year. 4 quarters make $1, right? So find the amount, and that's this. So we're going to just take this formula and fill in the blanks. We're investing $1,000, so that's the present amount. 1 is 1. The rate is 4%. We're going to use our calculator, of course, so we need to write that as 0.04. It's being compounded 4 times a year, so 4 goes down there, no relation to the 0.04. And as soon as I write that 4, I'll write a 4 up there too. And then it's times t, which is in years. In this particular example, it's 10. Put those in your calculator. See if you can do it in one step. If you don't get the right answer, go back and do it one piece at a time until you get the right answer. But go back. If you didn't get it in one entry, try it again until you can actually do that. It saves you time in the long run. There's the formula. There's the numbers being put in. Notice in this exponent, especially if you're using a TI-83, when you get out here to the end and you make your exponent, make sure you put the 10 and the 4 in parentheses, so it uses the result of that as the exponent. So if you do it one piece at a time, you would have that, and that's how much is there at the end of 10 years. With 1,000 deposited, 4% compounded quarterly for 10 years. And of course, the calculator just gave you 1488.86. Remember, it's in dollars. Next, same question, but how much interest did you get? Well, if you want the interest, we just found how much is there when you come back after 10 years. Oops. If you want the interest, you're going to have to take out how much you actually put in to begin with. You put in P dollars. You ended up with A dollars. The difference is how much interest was added in the meantime. We ended up with $1,488.86 minus our initial investment, and this is the interest earned for that period. Let's take a look at Becky. She has to pay a lump sum of $6,000 in 5 years. So this is a little bit different. Remember, the formula looks like this. Writing this a lot of times, this becomes second nature. The thing here is, we want $6,000 5 years from now. So where is the 6,000? A is the 6,000. So our formula looks like this. 6,000 equals. And P is how much money you put in. Well, it says how much deposited today. We don't know what P is. So we'll just put a P there. I wouldn't bother using X. I'd use P because that reminds me that we're looking for the original principal or the present value. And just put the rest of the numbers in. 1 plus rate is 3.1%. which is 0.031. It's compounded annually, so we'll just put 1 down here. And just to remind ourselves, we'll put that 1 up there as well. And it's after 5 years. So we have to solve for P. Now you could take those one piece at a time. You could write this as 6,000 equals P times 1.031 to the 5th power. Take 1.031 to the 5th power, divide it in both sides, and you get P. Or you can do it all at one time. I dare you to do this. So what would that be? Well, if we look at this formula as it stands right now with the numbers put in, we want P. P is being multiplied by this. If this were a 17, P would divide both sides by 17. So to get P, we'll divide both sides by 1 plus 0.031 over 1 to 1 times 5. Now this will be handy because you can put in 1 time and get your answer right away. You can also take a look in your calculator, see if it matches up with what you're trying to do on your paper, and then hit enter. So there's our formula. Put all the numbers in, evaluate part of it, and then divide both sides by that 1.031 to the 5th power. So using the calculator, if we want that 6,005 years under these conditions, you'll need to put in today $5,150.60. Now, this is a bit of a twist on it. Becky doesn't have that much money. She only has $5,000. But she needs $6,000 in 5 years. How can she get that? Well, what we've got now is that original formula and we have everything except the rate. We want to end up with $6,000 as our amount or maturity value. We only have $5,000 to put in. 1 is 1. We don't know the rate. And it says annual. That's going to make this a little bit easier. Put 1 there and 1 times 5. Then we're going to solve for R. Here we go. There's our formula. Put the numbers in. Six over 5. That's dividing both sides by 5,000. Remember, we had 6,000 equals 5,000 times this thing here. That's where the 6/5 comes from. 5,000 like here, and 5,000 there. So this becomes 6/5, just in case you got lost. Now, to get R, we're going to have to find R in a better situation. So we'll take the 1/5 power, or 5th root of both sides. So that's 6/5 on this side. We're going to take the 5th root of that, and we're going to take the 5th root of this side. Also, we could write it this way. Very handy. And then all we'll have to do is subtract 1 from both sides. And a bit of calculator work. unfortunately, because fifth roots are not fun. And Becky needs to find a bank or some organization that's willing to pay 3.71% for her $5,000, so 5 years from now she has the $6,000 she needs. One thing that's interesting is the greater the times interest is compounded, the more money we're going to get back. If it's annual, that does a good job for us. If our interest is compounded semi-annually, we'll actually end up with more money. If we compound it monthly, it's a little bit more. If we compound it daily, it's more. However, there is a limit. Compounding more often gives us more money. But it only gives us more money up to a point. And that point involves continuous compounding. So if you go from annual to semi-annual to monthly to daily to hourly to every second and so on, this is the limit. Continuous compounding. Now, if we take this formula for annual interest and make this n larger and larger and larger, what we'll find out is that the amount we get at first is bigger and bigger, and that makes us happy. But even compounding 1,000,000 times comes up against the limit. Almost $2.71 or 72 cents from the original $1 that we invested. This amount is called the Euler's constant. And let me write that for you, because Euler should be known by everyone. This is named after Leonard Euler, probably the most prolific mathematician of all kind. So how does it work? Well, if you invest P dollars like we did before with the regular compounding at this annual rate continuously, look for this, and for T years, it's always in years. Here is the formula you need. So compare that with the other one. You need to know both of them. Yes, you need to know both. This is for continuous, and I'll just call this anything other than continuous. Here's an example. First of all, notice that it says compounded continuously. So right away, you have a different formula. A, the amount or maturity value, equals the principal times E, that's Euler's constant, to the R times T power. Rate, the annual rate, T, number of years. All we need to do is put those numbers in that formula. There's our formula for continuous compounding. And there are the numbers thrown in. Now you don't need to memorize E. E is in your calculator. All you have to do is find it. I'm going to leave that to you. Just look for E in your calculator. Put those numbers in, and there you go. Continuous compounding for 5 years from that $5,000 at 3% interest, and you end up with $5,809.17. Notice that the daily compounding, once a day, using that old formula, the one we're going to continue to use, but the old formula, would have only given us a difference of 3 cents. Here's another one to try. 1,000 at 4% for 10 years gave us this amount. Remember that? Compare that with compounding annually, semi-annually, monthly, daily, and using the other formula continuously. Now, this is a very good excuse for you to stop right now and do these 1, 2, 3, 4, 5 small problems. This will give you an idea of how these compoundings actually work. Each one of these compoundings gives us a little bit more money. Now, I put some numbers in here, unfortunately, but remember, for this one, the n you're going to use in your formula is 1 because you compound it once a year. This one will be n equals 2. Monthly will be n equals 12. Daily will be n equals 365. Or for you obsessive people, 365.25. Continuously, we use the new formula, which is only good for continuous compounding. But use this one instead, using the 10 years and all the rest. Those should be your results. Take a look at how we got them. Notice this is the same as a 1 here and a 1 here. Notice the 2's here, the 4's here, the 12's here, and the 365's there. And of course, this uses an entirely different formula. Noticing each one increasing the compounding, you get a little bit more money, but only up to a certain amount, and that's with continuous compounding. Now we get to models. This is going to be short, but we're going to use them in the future. This is the model that you want to remember on the side. This is actually the one that we use with A equals P e to the RT. This K is going to be a constant. T is the time period. This is how much you started with. In the case of money, this is principal, and you could say this is the original amount, or amount at time equals 0. Here's an example we can use to get familiar with this. These are the amounts of carbon dioxide in the atmosphere, the concentrations. Make a scatter diagram of the data. Assignment. How do you do a scatter diagram with your calculator? Your scatter diagram on your screen will end up looking maybe something like this. Can you see that? How do you get that? See if you can find out by yourself. Actually try it. Use YouTube. It's easy to find. And then if you have tried, come to class, then we'll go over it in class as well. It's not really hard, but you need to put the numbers in. This is what they should look like when you're finished. Here's one model. It's not the only model, but it's one model for that data. Do you want to know how to find that? Well, it's pretty easy. Once you put those ordered pairs in, you can actually go in the calculator and say, hey, I want to do some statistics, and I want to do some calculating, and so on. Because you can actually make an exponential model, you can make a linear model, you can use a quadratic model, try a quadratic model, you can try a cubic model, and so on. Along with each one of those, you should get an R or an R squared value. The closer the R squared is to 1, or in this case R itself, closer to 1 or negative 1, the better that model is going to work for you. If you graph that actual model, you can compare how the model does. This is the model, and these are the actual points. Pretty close, aren't they? So this is a pretty decent model. If you also graph y equals 560 along with that, you can see where we've got an intersection point. Intersects at 2064.4 and 2130.9. This y value is how high this line is for this particular amount. Well, that's it, folks. A couple of short assignments for you, as well as the regular ones that you typically see. I hope you've followed most of this. What you haven't followed, write down as questions, bring them to class, and we'll finish up our job. We'll give a polish on your learning. All right? We'll see you soon. Keep smiling. Bye-bye.